Namaste and welcome back to the lecture on linear algebra through geometry. In the last class we looked at the linear maps in 3D where we looked at the idea of scaling, and we saw that scaling basically changes the volume of the geometry that you have, and then we also looked at the idea of reflections, and where we actually recalled reflections in 2D and we extended the idea to reflection in 3D, and this something that we saw as a reflection of a point about a line passing through the origin, but when we ended the class we had this question. So, what is the how do we look at the reflection of a point about a plane passing through the origin and orthogonal to a given vector. So, that is what we were looking at in the that is the question that we had when we finished the class last class. So, we will try to answer that and then we will go ahead with other type of linear maps and linear transformations, which includes shears and rotation. So, that is the agenda for the class today. So, let us get in. Okay. So, the question that we had was consider, so we are going to look at reflection about a plane passing through the origin and orthogonal to a given vector u, and orthogonal to a given vector u. So, this is what we are going to look at. So, let us see, let us try to understand this graphically. So, let us look at this. I have, let us say, this E1 axis, let us say E2 axis, and we have E3 axis. So, let us mark this. This is E1, this is E2, and that is E3. Now, I am going to look at a plane which is passing through the origin. So, this is basically assume that this is the plane passing through the origin. Let me call that plane as pi. This is the plane through the origin, and let us look at a vector which is perpendicular to the plane. So, I am going to look at this vector which is perpendicular to the plane, that is basically the vector u. This is what I am going to have, and let me take some other vector x, which is basically, let us take this. So, let us look at this to be the vector x. So, I want to look at the reflection of this vector x about the plane that passes through the origin and orthogonal to the vector u. This is what we need to find out, and for doing that, let me do a couple of things. So, what I will do is let me draw this vector u parallel to this itself. So, let me look at this vector u. So, this is also vector u. Now, what am I going to do? The reflection, as we saw in the case of a line, the reflection is going to be the midpoint of what would you call, that is going to be the midpoint of the line segment joining the vector x and the reflection of this vector x, which is basically, let me call that as RF of x about the plane. The midpoint of that is going to be, that is going to be, let us say, that is going to be the point q of x, which is given by the projection of x onto the plane q of x, right. So, now what we are going to do is I am going to have this vector x resolved into two components, one along this direction and one along the. So, basically I am going to have this component is already something that I know, because we were looking at the line passing through the origin and in the direction of let us say the vector u. So, we are going to call this as let us say the projection of the vector along that direction. Notation we have used in the same so we have used the same notation p of x in the last class. So, we will use the same thing, right. So, we are going to have the same thing. So, what do we observe here? We observe the following. We observe that okay, let us say x be any vector given by x is equal to, we are looking at x1, x2, x3, this is what we have. We basically want to find out the reflection of x about the plane pi. We want to find the reflection of x about pi, the plane pi. Okay. So, we can very clearly see that the vector v can be written as there can be the vector v can be written in terms of its components as projection of this v vector along the direction of u plus projection of this v vector x vector projection of this x vector along the direction of the plane pi. This is what we have. So, let us, that is nothing but we are going to call this as p of x plus p of let us say the projection along the plane. This is also something which we saw in the previous class when we looked at the distance from a point to the plane. We had used this notation which is basically q of x. So, we have this q of x, right. I mean if you really want to understand what this means, let us just look at a simple example. Let us consider this example. I have let me have this vector which is let us say v1, v2, v3, and I am going to call this vector u as basically along the direction of E1 which is 1 0 0, and the plane pi is basically given by the what do you call, the plane pi is basically the x2 x3 plane, right. The plane pi is the x2 x3 plane. So, what are we going to get? We are going to get v is equal to v1 0 0, the projection along the direction of u, plus 0, this is a component of vector which is along the plane which is v1 v2 v3. So, this is what we have. So, that is exactly what we are trying to do. We are going to call this as the p of v and we are going to call this as q of v. Yes. So, that is what it is. So, let us write this. So, in that sense we understand that in that sense what we understand, we basically understand that this is the vector x can be what do you call broken down into two components, as I said, one along the direction of u and another one along the direction of pi. Okay. So, where p of x is basically projection of x along u, right, and q of x is projection of x onto the plane through origin and perpendicular to u, right. So, this is what we have. Again, let us use the same principle that we did for the case of projection reflection about a line. So, what we are going to do is let r pi of the vector x denote the reflection of x, denote the reflection of x about the plane pi. So, we already know that for any x, the midpoint of the line segment joining the vector x and the reflection of this vector x r pi of x is the projection of x onto the plane, is the projection of x onto the plane pi, which is given by q of x. So, therefore, what we have q of x is nothing but half of v plus the reflection of half of x plus the reflection of the vector x about the plane pi. So, half r x plus r pi of x is what we have. Therefore, what we have is r pi of x is nothing but 2 times q of x minus the vector x, right, where q of x is basically defined from. So, where q of x can be found out as x minus p of x, where p of x is basically the projection of the vector x onto the normal to the plane pi, which is passing through the plane pi passing through the origin, right. So, this is what we have. So, this is basically the reflection. So, reflection of a point about a plane passing through the origin and orthogonal to a vector u. So, let us write that very clearly. So, let us do this. So, reflection of the vector x a about the line passing through, about a line passing through the origin. Let us take this, about a line passing through the origin, that is basically given by r f of x is nothing but, we already saw that this was 2 times the projection of the vector x along the direction of u minus the vector x. Now, reflection of x about a plane passing through the origin, plane passing through origin and orthogonal to the vector u, is given by r pi of x is equal to 2 times q of x minus x vector, and in this case reflection of about of x about a line passing through the origin and in the direction of u, in the direction of u, a vector u, right. This is what it is. So, P of x denotes projection of x in the direction of u. Right. So, now we know the difference. Q of x is basically projection of x onto the plane pi. Right. So, that is what it is. So, we could probably even quickly take an example and see what it is. Let pi be the x1 x2 plane. So, the vector u perpendicular to the plane will be the vector along the x3 axis, which is 0 0 1. Now, I want to find out the reflection of v, which is given by 1 2 3 about this plane. So, reflection of v about pi is what we want to figure out. So, what are we going to do? We are going to look at this. So, we know that r pi of v is given by 2 times q of v minus the vector v itself, but we know that the vector q of v is nothing but the vector v minus the vector p of v, that is the projection of vector onto that axis u, where p of v is projection of v onto u. So, which implies projection of that vector if we take. So, v vector is 1 2 3 and the projection of that vector onto the projection of v onto that axis is going to be what are we going to get? Projection of this is going to be 0 0 3, right. We are going to get 0 0 3. So, we know that r pi of v is nothing but 2 times q of v minus v, which is nothing but 2 times, we see this is 1, 2 minus 0 is 2 and 3 minus 3 is basically, so we have this, let us write this first of all. So, this is going to be 1 2 0. So, I am going to have 0 minus 1, the vector v is like minus 1 2 3. So, I am going to have 2 times 1 minus 1, which is 1, 2 times 2 4, 4 minus 2 is 2, 2 times 0 minus 3 is basically minus 3. Oh, that is exactly what we see here. 1 2 minus 3 is the reflection of this vector v about that plane, let us say x1 x2 plane, because if you look at this intuitively also you see this x1 x2 plane, basically it separates the negative z axis with the positive z axis, and therefore, the reflection is basically minus 3, only that component changes here, right. The next linear transformation or linear map that we are going to look at is the idea of shear. Recollect that when we did shears in 2D, we basically looked at one important application of shears in 2D, which was basically converting regular font to italics and taking the inverse of that, you get italics to the regular font, that is what we had. So, even in 3D we have shears to be possible. So, what we I mean how do we interpret the idea of shears in case of 3D. So, let us look at that. Recall again, in 2D the shear transformation, basically the shear map or shear transformation takes a square to a parallelogram. So, what happens in 3D? In 3D, shear takes a cube, shear takes a cube to a parallelepiped. That is what we have. Right. So, we know the idea of shear. In 2D it was like, say you have two components x1 and x2, the resultant vector that you wanted out of that was basically, it could be x1 plus say some component alpha times x2 component, or it could be the second vector x2 could be the second component, or the transformed vector can have a component which is x2 plus say some alpha times x1, and that is what we looked at. In 3D also that is possible. So, let us just look at this. A 3D shear map, for example, I have this vector which is, let us say x1, x2, x3, this x vector, and I want to get this vector which is basically, let us say x1 plus x3, x2 plus x3 and x3. That means the x3 component is fixed, whereas you have shears along the x1 and x2 component. So, what is the matrix that does this? So, I need to know what is the matrix that does this. Like how we did in the previous case, we can figure out very easily that if you look at the identity matrix, the transformation that you do is basically with respect to the identity matrix. So, I have x1, x2, x3 which is equal to x1 plus x3, x2 plus x3 and x3, which means the third component is not going to change at all. So, I am going to use this as 1, third component does not change. So, this is what it is going to be. Now, what about the first component? The first component is basically x1 plus x3, which means I have this. The second component is basically x2 plus x3. So, I have this, right. So, this is what we have. This is basically the idea of shear. Always remember, when we did even the in case of 2D, where when we did the shearing operation, we found that the height did not change and the base did not change, it only had a shear. That means it preserved the area. In this case, we are going to say that shears are going to preserve the volume. So, let us take another example. Let us take consider this example. So, example, let the vector x be equal to x1, x2, x3. Now, I want we want to get another vector which is, let us say the vector x prime, which is given by x1 0 0. One way to obtain this is basically project the vector x onto the even axis. You basically get x1 0 0, but you know that the linear transformation like shear and all is basically an invertible transformation. So, what we want to do is we want to do this through a shear. So, the question is, can we get a shear matrix that transforms x1, x2, x3 to, let us say, x1 0 0. So that is a question that we have. So what is it that we have? We have this x1, x2, x3. I am going to get x1 0 0. So this is the matrix that I am looking for. If you look at this, let us say again x1, x2, x3, I want to get x1 0 0. You see the first component of the resultant vector is the same as the vector x1, x2, x3. So I will retain the first component as such, nothing changes there. The second component has to become 0, the second component has to become 0, and I have to get a shear matrix, which means this, let us say my x2 remains the same, which means I have x2, but I want to get a 0 here. So how do I get a 0 there? I can do one small stuff here. What is that? If you look at this, I have to add something to the x1 and I have to get plus x2 to be equal to 0. What is it that I can do? I can do this business. I can do minus x2 by x1. If I do minus x2 by x1, what do I get? When I multiply this, I get minus x2 by x1 into x1. So x1 gets knocked off. So I get minus x2 plus x2, which gives me 0. Similarly, I want to look at the same thing happening with x3. I want to get this x3, this component to be 0, but through a shear. So how do I do this? I can add minus x3 by x1 to the first column, 0, the first element 0, and then if I do 1, so I get minus x3 by x1 into x1, which is basically minus x3 plus x3, that gives me 0. Now the question is, where do we use such a matrix? Where is this matrix used? I am quite sure when we did the idea of Gauss elimination, we looked at Gaussian elimination. We wanted to make the elements below the, if it is the first column, we wanted to make the elements below the first column, first element to be 0, and for that we had done some elementary row transformation, where we said like R2 minus 2 times R1, R3 minus 2 times R2, R1, and so on. This shear, that is exactly what you are trying to do as shear. So this matrix is going to help you effect that elementary row operation in Gaussian elimination. So Gaussian elimination, so useful in Gaussian elimination, right. So this is basically the idea of shear, and we see this. Okay, let us look at the what would you call it? So the next question that we have is, does shear preserve volume? This is something which we wanted to check. Let us see if shear actually preserves volume. In 2D, when we basically looked at the area of a, let us say you had the unit square where the area was 1, and then you sheared it with something else and you still found that the determinant to be the same. That is exactly what we have here. So for example, if you look at this matrix, which is like say 1 0 A 0 1 B 0 0 1, which is basically going to give me this vector, let us say x1 x2 x3. So I am going to get this matrix, the resultant vector is going to be this x1 plus A x3 x2 plus B x3 and x3. This is what we are going to have. Suppose if you are going to look at transformation of a unit cube from here, you will see that the volume is basically preserved. Okay, so the volume is preserved by shears. As I said before, you will see that the shear operation does not change. So shear does not change, the base or the height. I mean at least this is very evident when we did in let us say in case of 2D we could see this. So, since it does not change the base or the height, what we are going to say is preserves the volume. Right. So, so two of the most important linear mappings that we have studied here, one is the reflection about the plane, and then we looked at the I mean reflection about the plane passing through the origin. We also looked at recall the reflection about a line passing through the origin, and then we looked at the idea of shears. And shear in 3D we also looked at its application in Gauss elimination technique, where we want to make the elements below the pivot elements to be 0, which we did in case of Gauss elimination for solving system of equation, and that is what we saw here. So, the next question that we have is, how about rotations in 3D? How about rotating a vector or rotation transformations in 3D? What happens to the rotation transformation in 3D? And I mean we had already seen the notion of rotation in 2D. We will be recalling that, and then we will also look at the notion of rotation in 3D. We will follow that up with the idea of determinant of a matrix, which is basically the volume of the parallelepiped. We are going to look at certain properties, and then we are going to look at eigenvalues and eigenvectors as far as a 3D transformation is concerned. So, the agenda for the next class is basically looking at rotation transformations in 3D. We have already studied projections, we have studied reflection, we have studied shear. We will be studying rotation in the next lecture, follow it up with the idea of determinants and so on. Thank you.